Hi, my name's Matt. I'm with Fluke Corporation. We're coming to you today from American Fork, Utah at the Hart Scientific Division of Fluke. I work in the Primary Standards Lab, where among other things we make the triple point of water cell that I'll be showing you today. Triple point of water cells are used in labs throughout the world to calibrate and maintain precision thermometers. What we're looking at right now is very pure water, sealed of course, and at Fluke we control not only the purity of the water, but the isotopic composition of the water to a point where, when properly prepared, this cell will provide a reference temperature for you of exactly 0.010 degrees Celsius with an expanded uncertainty of 0.1 millikelvin, or in other words, an uncertainty of 0.0001 degrees Celsius. I'm calling it a triple point of water. What we're seeing right now is water as a liquid and water as a gas or a vapor. There is no residual air in here. That was removed during the sealing process. Obviously, to make a triple point, we'll have to introduce the third phase of water, solid. So we'll do that by freezing an ice mantle. I'll show you an easy method you can do with very easily accessible materials. In front of me, I have a bowl of ground up dry ice or frozen carbon dioxide. I have a spoon to scoop it with. I have a wire long enough to go into the well of the cell and stand there. If you don't have one, a paper clip can be used. You can bend it into that highly scientific shape there and just hang it in the top, but we won't. I have a bottle of alcohol. We're going to use the alcohol for a catalyst or a thermal conductor. I have here ethanol. Methanol will work. The isopropyl alcohol you buy at the drugstore probably wouldn't be good. It has a lot of water into it. We're going to put 4 drops of alcohol into the well of the cell. 1, 2, 3, 4. If you use too much alcohol, well, I'll show you what might happen, or at least we'll talk about it. I also have a glass rod. If you buy one of our cells, this comes with it. It has a number of uses, but I'll talk about them in a moment. Now, we want to freeze an ice mantle. An ideal ice mantle will be frozen from the inside out. That will freeze the purest of the pure water first, and any impurities that may be there will pushed out. I want my mantle to be uniform, meaning I would like it to be the same size down at the bottom as it is up at the top. That's a challenge, but we're going to try. To do that, I will attempt to fill the well all the way to the top with dry ice rather than stacking it up little by little. If we do that, we'll get a teardrop shape. This cell has been pre-chilled. If the cell is room temperature, it won't work for you. You can do that in a refrigerator, in a maintenance bath, in an ice bath. I wouldn't recommend you use the freezer section of your refrigerator. You might freeze the cell and break it. Let's get started. Let's try to fill it to the top. Dry ice will spill. That's okay. It evaporates into gas and won't leave a mess in your lab. Spilling is all part of the fun. You see the boiling action that's going on in there? 2 things to say about that. One is, now we know the purpose of this wire. Most of that dry ice will brush against the wire, break up, and fall down back into the well rather than spill out onto your work surface. If I had used much more alcohol than the 4 drops I used, we would be getting a lot more agitation than we're seeing. So this is a pretty good amount. And you can see trying to fill the well up with dry ice is a constant challenge. It's not something you can do and walk away from. This is fairly labor intensive. The glass rod is in case I get a big air bubble down here, I can very lightly tamp the dry ice down. You don't want to pack it. This isn't a muzzle loader. It's fragile. Now, I'm starting to see forming what's called an ice bridge, but that means I've got solid ice freezing from the well right to the outsides. When that begins to happen, you need to warm it up and melt it away. If you let it go unchecked, it will break your cell. A little bit of agitation is okay. If the agitation is side to side, I do not want to rotate this cell quickly. There is ice freezing to the well. You can probably see that already. If you start rotating it quickly, the weight of the ice that's frozen to the well will crack it open and break your cell. I do this live in seminars a lot. It's a hands-on demo we do in our seminars, and I'm often asked, how many of you broken? Just one, and it was from rotating when I thought that the mantle hadn't, or I thought the mantle had melted away from the cell, from the well, and it hadn't. One of the most commonly asked questions is, how do I know when I'm finished? Or how thick does that ice mantle have to be before I can use it? The scientists I work for like to throw out the number 8 millimeters. We want your ice mantle to be 8 millimeters thick. Well, I haven't figured out a way to open that up and measure it with a pair of calipers. The ice mantle looks bigger than it is. We'll demonstrate that in a minute. We'll show you what I'm talking about. But we have a little bit of parallax. We have optical distortion because the cell is round, so it's magnifying the ice mantle. It will look like it's touching the sides of the cell before it really is. Personally, I like to get the ice mantle as large as I can without touching the sides. Ice bridge forming again. If the ice mantle gets so large that it's touching the sides, it might grow and break the cell. Again, we don't want to do that. Melt the ice mantle. So the question will come along, how do you know when it's big enough? As this gets a little larger, we'll show you something you can do to look at it without the parallax, without the optical distortion. Another question I'm often asked, we can talk about this while we're freezing it, is how long will it last? Well, if you just leave it out in room temperature, it'll last about an hour or less. You can maintain, got another chunk of ice there. You can maintain an ice mantle in a bath or a dewar. If you have a nice dewar, you can put crushed ice and water in there, move the cell into the ice bath, and it will last about 8 hours. If you only had a day's worth of testing you needed to do, that would be all you needed. I use these almost every day in my work. We make maintenance baths that we can store these in and use them in. And once I get the maintenance bath properly set, once I get the temperature properly set, I can maintain an ice mantle for weeks. Probably about 6 weeks before I need to refreeze it. So that leads to the question, well, what's the proper temperature of a maintenance bath? Well, as you recall, I mentioned that the triple point of water coexisting as liquid, solid, and gas, is 0.010 degrees. An ideal temperature for a maintenance bath is 2 or 3 millidegrees lower than that, so maybe 0.007. Now, of course, you can't do that just by looking at the display on the front that tells you the temperature. Those are only accurate to a quarter, maybe half a degree. You'll have to take some sort of a temperature probe, measure the bath, measure the cell, see what the difference between them is, make the minor adjustment to the bath, measure the cell again, see what the difference is. But that method works very well, having it just a couple of milli-K lower than the triple point of water itself. Around the bottom here, you can see some stress fractures within the ice. That's normal. We're freezing the ice very quickly. It's bound to build up some stress. And that stress relieves itself by the ice cracking. It's not the cell cracking. Sometimes it makes a sound that sends a chill through your heart and you're afraid you've broken your cell, but you haven't. It's just the ice. Also, one other step before you can use the cell, what we have right now is ice frozen solid to the well from top to bottom. If we were to put a unit under test in there right now, kind of melt an ice bridge, what we would be measuring is a block of ice. We wouldn't be measuring the triple point of water. Before we use the cell, we need to melt that ice mantle away from the well just a little bit. I do that every morning before I start taking measurements with these. I need to do that inner melt so that the ice mantle is floating freely around the well and isn't frozen to it. There are a couple of methods to doing that. One is to introduce this glass rod into the cell. Just put it into the well, and within about 20 seconds it usually will have warmed things up enough that that ice mantle is floating freely. If it's frozen very badly, you could maybe pour in some room temperature alcohol, and that will melt the ice away from the sides. Metrologists who want the best uncertainty possible, after freezing this ice mantle, will put the cell in a maintenance bath and they will let it sit overnight. I mentioned, we talked about stress fractures, and we mentioned that the ice freezing so quickly is what's causing the stress. That will actually impact your temperature, the reference temperature that this generates. By letting it sit in a maintenance bath overnight, the stress is relieved in the ice. That impact on the temperature goes away and you'll have the smallest uncertainty possible. If your uncertainties are relatively high, you can start using it right away. Like I mentioned, you could put it in a dewar of ice water and start using it right away and use it throughout a work day. And for some people, that's all they need. They've got maybe a standard or two, or 3 or 4 that they need to check maybe once a month to see how they're doing. So having a working triple point during one work day is enough for them. I think I mentioned I use them daily. I use several of them daily, and so I need a maintenance bath to maintain them for a good long time. The colder your hands get, the harder it is to melt the ice bridge away. All right. You've also noticed I have a beaker full of water here. Let's move it a little closer. I was talking about how the ice mantle that we're seeing in there looks larger than it is. As I sit here and look at it, it looks to me to be just a couple of millimeters away from the edges of the cell down here. I can remove the parallax, I can remove the optical distortion by setting this in a beaker full of water. Everything is magnified, but it's magnified equally now. And we can see there's still quite a gap between the ice mantle and the sides of the cell. Now, sitting here talking and showing you things, I'm neglecting my duties of keeping that well full of ice. So we're getting kind of a teardrop shaped ice mantle. I have one that I froze yesterday. It spent last night in a maintenance bath. And I'll show that to you now. All right, I've got it in a dewar full of ice water down here so that the ice mantle doesn't melt. You might be able to see as I rotate the cell, The ice mantle is only rotating with it a little bit. It's mostly free of the, I see we've melted a little bit of it away at the bottom. That ice mantle looks like it's touching the sides of the cell. It is not. If we put it in here, you can see there's still quite a gap. But it's close, and in a properly set up maintenance bath, it will last a long time. I said about 6 weeks. You can also see the ice mantle does not have a glass-like surface texture. After sitting overnight in a bath, it has a little bit of a visible texture to it. The longer they stay in there, the more of that texture you see. You almost get a cottage cheese-like bumping throughout the ice mantle. And when it's not good anymore, it starts to break apart. When you see your ice mantle starting to break apart, you can't use it anymore. If you see that it's melted away from the bottom and you only have ice down to here, you can't use it anymore. Same with the top. If it melts away from the top, you've ruined your uncertainties, and you should refreeze it before using it. So to summarize, we started off with a pre-chilled cell. We put 4 drops of alcohol in the well to act as a thermal catalyst and start the freezing. We tried to keep a full well of dry ice in an attempt to have a uniformly shaped ice mantle. When ice bridges began to freeze, we melded them with our hands to prevent breakage. Now you know all there is to know about realizing an ice mantle in a triple point of water cell.